Just like with regular complex numbers, we can compute products and quotients of complex numbers in polar form as well, but it's a little bit trickier than if you're just multiplying a plus bi times a plus another bi. Let's look and see what happens if we take z1 times z2. That's going to be equal to r1 cosine theta 1 plus I sine theta 1 times r2 cosine theta 2 plus I sine theta 2. Well, then we multiply r1 times r2, but then we have some foiling to do with the trigonometric functions. So z1, z2 is equal to r1, r2, but we still have cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. Foiling, we get cosine theta 1, cosine theta 2, and that does not become cosine theta 1, theta 2. That's cosine of theta 1 times cosine of theta 2, plus I cosine theta 1 sine theta 2, plus I sine theta 1 cosine theta 2, plus I squared sine theta 1 sine theta 2. I squared is equal to negative 1, because remember, I is defined as the square root of negative 1. So if you square both sides, you get I squared is equal to negative 1. That means we have z1, z2 equals r1, r2, cosine theta 1, cosine theta 2. I'm going to put the sine theta 1, sine theta 2 next with a minus sign because that I squared is a negative 1. That's minus sine theta 1, sine theta 2, plus I times cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. I just factored out that I from both of those terms. The cosine of theta 1 times cosine theta 2 minus sine theta 1 sine theta 2, that's like cosine u cosine v minus sine u sine v. And that is the sum formula for cosine. Cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2, that's cosine u sine v plus sine u cosine v. And that is the sum of sine. So z1, z2 is equal to r1, r2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2, using the sum and difference formula to replace those. You can prove the quotient the same way, but the quotient of z1 over z2 is equal to r1 over r2 times the cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. And in this case, z2 can't be 0. Defining z1 and z2 the same way that I did, then the product is r1, r2 times the cosine sum plus I times the sine sum. And then the quotient is equal to r1 over r2 with the cosine difference plus the I sine difference. So division has the difference and multiplication has the addition of those two, where it's cosine first as the real component and sine as the imaginary component. If we wanted to compute powers of complex numbers, that's basically saying we want to take z to a higher power. Let's say I wanted to take z squared. That's the same thing as z times z, and so I could use the product formula above, where z times z would be equal to the r times the r times the cosine of theta 1 plus theta 1 plus I times the sine of theta 1 plus theta 1. And then if I wanted to take z to the third, I'm then going to need to multiply that by another r cosine. And it gets trickier because then you're dealing with more sum and difference, and so we need a shortcut. We're going to use de Mavros Theorem to help us when we have higher powers. Instead of having to take 2 and then multiply by a third, we want to be able to use a formula. So if you have z to any power n, that's the same thing as r times the cosine of the angle plus I sine of the angle to the n power. And I can distribute that n, that becomes r to the n times the cosine of theta plus I sine theta to the n. This can be rewritten as r to the n times the cosine of n theta plus I times the sine of n theta. So instead of having n be a power of cosine, we're looking at a multiple of the angle. And it comes back to the sum and difference of where we get multiples. So this was n equals 2, because we're talking about squared. We would have 2 thetas then, because you're doing theta plus theta. So here is the theorem and how you would raise to a higher power. The last topic we're going to cover in this section is finding the roots of a complex number. The nth root means, do I want to find 2 roots? Do I want to find 3 roots? And so on. So the nth roots is if we have some number, z, equal to r cosine theta plus I sine theta. So for any root, like if I wanted a square root, cube root, something like that, I can use the formula below. If I want to find cube roots, then n is 3. And so I'm going to take the cube root of whatever my r value is times the cosine of my theta plus 2 pi k over 3 plus I sine theta plus 2 pi k over 3. So whatever my root is, I use as my n. The k values are used to find the different roots. For instance, if I'm looking at third roots, then my k is going to be from 0 up to 1 less than the root. So k is equal to 0, 1, 2, up to n minus 1. So if we have 3 roots, we're going to use k equals 0, 1, and 2 to find the 3 different values. So you would use the equation where you would have 3 times r cosine of theta plus 2 pi times 0 over 3 plus I sine theta plus 2 pi times 0 over 3. That's going to be with k equals 0. You need to do it again for 1 and for 2 to find the cube root of this value. So you would take the cube root again for each of these, times the cosine of theta plus 2 pi times 1 now for k, plus I sine theta plus 2 pi times 1 now for k, where the 3 doesn't change, because that's the number of roots that I'm asked for. It's the k that's changing when you are finding your different values. So whatever power you're talking about, you have that many solutions for k, or that many values of k that you're using. It just starts at 0. So if you're talking about 3 roots, you have 0, 1, and 2. 6 roots, 0, 1, 2, 3, 4, and 5. Okay? You can write your answer using 360 degrees, or you can use 2 pi, depending on how they ask you to solve. Sometimes you'll be asked to use degree measures for the argument. Sometimes you'll be asked to use radian. It's dependent on the way the question is worded. And that's it for this section.